Okay, so the concept of relative masses, I think, is sometimes easiest understood if you think about it in terms of candy instead of particles when we get started. So imagine that you were looking at three different bags of candy, each of which, so bag one of each candy was 1 liter in size. And if you recorded their mass, and the 1 liter bag of candy A pieces weighed 600 grams, of candy D weighed 800 grams, and of candy G weighed 900 grams. And then let's say you compared a second set of bags. Each second set of bag was only a quarter of a liter. And what you saw there is that naturally the mass was 1/4 what it was before. But once again, the masses compare to each other in the same way. So a quarter-liter bag of candy A is 150 grams, candy D is 200 grams, candy G 225. And then finally, you have a third set of bags. These are now 2-liter bags. And so the masses of candy A, 2 liters is 1,200 grams, candy D, 1,600 grams, candy G, 1,800 grams. So if this was the case, you're comparing these three bags and these three different candies, it seems like no matter what size of bag, the volume of the bag, the masses of the different candies they have the same relative masses compared to one another. The ratios, how their masses compare, are always the same. And so from that, you might say to yourself, well, we've got, move those up, we've got A, we've got D, and we've got G. And if we want to compare these ratios and kind of simplify them, the best way to do that is to divide every mass by the smallest mass. So 600, for example, divided by 600 equals 1. 800 divided by 600 gives you 1.33, or 1 1/3. And 900 divided by 600 gives you 1.5. Now you'd get those same results if you did 150 divided by 150. That would get you 1. 200 by 150, 1.33. 225 divided by 150, 1.5. So it doesn't matter actually which bags you use to come up with your relative masses, because no matter the size of the bag, the masses of these types of candies seem to compare to each other in a very particular way, in a very particular ratio of mass. So 1 to 1.3 to 1.5 is fine. We could use those values as thinking of as the relative masses of A to D to G. We could also make them whole numbers if we wanted to make things slightly simpler. So 1 to 1.3 to 1.5 is the same as 6 to 8 and to 9. So these values here are the relative masses of candy A to candy D to candy G. Now notice in none of these cases have we actually counted individual pieces of candy. So I actually don't know how much an individual piece of candy weighs for any of these things. I just know that if I say that A weighs 6, then relative to that, D weighs 8. And relative to that, G weighs 9. So I don't really care how much the individual pieces weigh, because I'm always going to be dealing with more than one piece of candy. All I really care about is how they compare to each other, how much they weigh relative to each other. And so that's what I've got here, 6, 8, and 9. And that's what we'll use going forward, as thinking of them as sort of the mass of each type of candy. A weighs 6, D weighs 8, and G weighs 9 relative to each other. Okay, so relative masses are going to be used in two ways. They're going to be used in calculations where you are figuring out the percentage by mass of different types of candies in a mix, or where you're figuring out the number of pieces relative to each other, the ratio of pieces in a mixture. So here are a couple of the simplest examples that we can come up with. If you are given the ratio of pieces of types of candy in a mixture, all you have to do is times the value in the ratio by the relative mass, and then convert those mass values to a percentage by mass out of 100%. So here's what that means. If you were told that you had a mixture where you had 2 A pieces for every 1 D piece, right? Then we could say, all right, 2 A's for 1 D. This is one way to write a ratio with a colon. As a formula in chemistry, we're going to see the same thing represented like this: A sub 2 and then D. So that tells us 2 A's for every 1 D. Okay, well, that ratio tells us if there's two A pieces and one D piece, and if each A weighs about 6, and we'll say 6 grams per piece, even though we know it's not really grams, but doesn't really matter. We're going to keep that consistent just to give us a unit. So if we had two A pieces for every one D piece, and every A piece weighs about 6, then 2 times 6 would give us 12 grams that's from A. And if we had one D piece and every D weighed 8, then we'd have 8 grams that came from D. And so the total mass of this mixture would be 12 plus 8 would be 20 grams. So what percentage of that is coming from the A? Well, just take the part that is A, 12 grams, divide it by the total mass, and technically you have to times that by 100 to make it this whole number percentage, but you would get 60% is A. If I did the same thing with the D, 8 grams divided by the total mass, which is 20, I would get 40% of the mass is coming from D. So notice that we had a 2-to-1 ratio in terms of the number of pieces, but we actually have like a 6-to-4 ratio in terms of the mass, because the pieces don't weigh exactly the same. So just because I have a 2-to-1 piece ratio, I don't also have a 2-to-1 mass ratio. That's why these are two different concepts, percent by mass and the ratio of the actual pieces of candy. Now, just because the ratio was 2-to-1, I don't have to use 2 and 1. It's the simplest thing. It means I don't have to change the number. So long as I keep that ratio the same, I'm always going to get the same answer. So for example, on the right here, I've just used slightly different numbers. So I've kept the correct ratio by doing 4 pieces of A and 2 pieces of D. Now, if I take those times by the mass, that would mean 4 pieces would give me 24 grams of A. 2 pieces of D would give me 16 grams of D. That would make the total mass 40. And so 24 out of 40 is still 60% A by mass, and 16 out of 40 is still 40% D by mass. So it doesn't really matter which numbers we choose to carry out this process. So long as we keep the ratio the same, the ratio that we're given in the question, we should get to the same percentage by mass values. If we take this same example, but we flip it, and now let's look at what would we do if we started with 60-40 by mass and we had to figure out the ratio. Well, just imagine you're basically going to do it backwards. You're going to take those percentages and you're going to convert each percent out of 100% to a specific amount of mass. Because in the previous example, you were given a ratio of pieces. Well, when you're given percentage by mass, you're really given a ratio of masses. Then once we've got our mass amounts, you're going to divide instead of multiply by each relative mass. And then we're going to simplify the ratios to get simpler whole number ratios. So if I know that I have a 60% by mass A and a 40% by mass D mixture, well, the simplest thing to do is just say, well, if I had 100 grams, that would give me 60 grams of A, and it would give me 40 grams of D, right? That's following the correct ratio, 60-40 of mass. I don't have to use 60 and 40. I could also use 6 grams and 4 grams. I could use 3 grams and 2 grams. It doesn't really matter. So long as I keep the correct ratio, I will always end up with the correct answer. So the simplest thing to do is just say, out of 100 grams, that would mean 60 and 40. Then all I have to do is get rid of the percent sign and put a gram sign. Well, if I had 60 grams A and 40 grams D, that would mean that I had 10 pieces of A for 5 pieces of D, because 60 divided by the mass of each A, which is 6, gives me 10. 40 divided by 8 gives me 5. And so that would tell me that if I've got this ratio of masses, that gives me a ratio of 10-5. And if I simplify that by dividing, 10 divided by 5 gives me 2, which means the real ratio, the simplified ratio, is 2-to-1. Right? There's 2 A's for every 1 D. Notice that if I used different masses, I would end up with the same ratio. 6 grams and 4 grams is still 60% and 40%, divided by the relative mass of each piece. So 6 divided by 6 is 1 A. 4 divided by 8 would be half of a D. So if there's 1 A for half of a D, when I divide that, I'm still going to get the number 2. And that means 2 per 1, 2A for every 1 D. So again, it doesn't, like in the previous example, when you're given a ratio, it doesn't matter which actual numbers you choose to use, so long as you follow that ratio and then simplify, you'll always get to the same answer in the end. Let's see this with another example. In this case, you get 1A for every 1G. So this is the pieces. Okay. Well, 1A, 1G, you could also do 10 A's per 10 G's, 100 A's for 100 G's. It doesn't really matter. So I'll look at the one on the left here. 1 times 6, there'd be 6 grams coming from A. 1 times 9, there'd be 9 grams coming from G. The total mass would be 15. Therefore, 6 out of 15 is 40% A, and 9 out of 15 is 60%, and I should say G. Fix that. Okay, and again, if you did 10 and 10 times 6, you get 60 and 90, total mass of 150. So you'd still get 40% and 60%. So this is how you'd solve for percent by mass. And now if we flip it to start with masses and go to pieces, in this example, instead of starting you with percentage values, which you turn into gram values like you did in the last example, I've actually just started you with gram amounts. This is a little bit more similar to what you would see in an experiment in class. So if 0.148 grams comes from A and 0.222 grams comes from G, just skip the first step. You don't have to convert percents to grams anymore. Now just go straight to this step. Divide the gram amounts by relative mass amounts. So 0.148 divided by 6 gives me 0.0247. Now at first that seems really confusing, like how can you have this much of an A piece? And the idea is it doesn't really matter what the number is on its own. What we care about is how the number of A's compares to the number of G's. We're trying to find a ratio. So you can't get too hung up on what the actual number means. It really only matters in terms of how does it compare to the other number. And you'll see that when I take 0.222 divided by 9, I actually get the same number, 0.0247 G pieces. And so what we see in the end is that the number of A pieces is exactly the same as the number of G pieces. So 0.0247 divided by 0.0247 equals 1. And that tells me it's a 1-to-1 ratio. So that's really what we're trying to get to here. We're trying to get to the ratio, or really the formula, AG, 1-to-1. Right? So notice that whether I start with the ratio and then I get to the percent by masses, or I start with masses, I can get back to the ratio. Okay? In one of them, you multiply by the relative mass and then turn it into a percent. In the other one, you turn it into a mass from a percent, and then you divide by the relative masses and simplify the ratio until you get whole numbers. One final example where there are 3 things given. Okay, so now we've got percentage by mass for 3 different candies for A, D, and G. The simplest way to deal with that is keep the ratio the same and just make those percentages into grams. So 31.6% becomes 31.6 grams of A, and so on. Divide each mass by its relative mass, and that gives you the number of A's compared to the number of D's compared to the number of G's. Remember, we don't really need to think of it as that there's 5.27 pieces of candy A. What matters is the numbers relative to each other. The way you deal with this is like you did before, but now you've got 3 different examples. Divide all 3 values by whichever one is smallest. In this case, this is the smallest value, 2.64. So 5.27 to 2.64 in a calculator would essentially give you 2, right? Which means that the ratio is 2 A's for every 1 D. If you compare D to itself, 2.64 to 2.64, obviously that's going to give you 1. Obviously, it makes sense that there's 1 D for every 1 D. And 5.27 on the G, and that should be, sorry, let me fix that. Okay. 5.67 G divided by 2.64 D again gives you 2, which tells you there's 2 G's for every 1 D. So when you get these numbers here, you compare everything back to the smallest number, and you are now going to get the whole number ratio, or at least you're going to get the ratio per 1 of this thing D that you had the least of. So it's 2 to 1 to 2 is the ratio. A2 D G2 is how we'd write that as an empirical formula, chemical formula. You'd have 2 A's for 1 D and for 2 G's. So the steps are the same if there's 3 or more things. Really, 3 is about the most. I suppose you could have one where you have 4 things. I've seen that before, but the process is the same. Percent, make that percent as a gram amount. Remember, this is just a ratio of masses. So we could pick any amounts, but we've chosen these values because it's simplest to just make the percents into grams. Divide each mass by its relative mass to get the relative number of pieces, and then compare the numbers to each other to get the whole number ratio of pieces. 2 to 1 to 2 is the ratio of pieces. And from here, we're going to go on to this actually in terms of atoms and molecules and actual chemical formulas, but the concept remains the same, that the atomic masses are really relative masses. They tell us how the elements compare to each other in terms of their mass, and we can use those values to eventually figure out chemical formulas and to figure out percentage by mass for actual compounds, dealing with carbon, hydrogen, and so on. But the process is going to be exactly the same as when we're dealing with candy.